1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Time to stream, time to stream. It's streaming time, streaming time. Okay, hey everybody, welcome to the stream. And I think things are going well. And yes, I can make a note. It's time to do the stream. So the questions, if you have any other questions you'd like to see me, drop them into the chat. Otherwise, we're doing the questions listed below, page 103, chapter 3, question 53, 37, 39, 41, 69, 75, and 5 and 7 on page 131. Let's do it. Question 53. 53 goes like this. A skier is gliding along a 3 meters A skier is gliding along at 3 meters per second on a horizontal frictionless snow. He suddenly starts down a 10-degree incline. His speed at the bottom is 15 meters per second. What's the length of the incline? How long does it take to reach the bottom? All right, so if you haven't noticed yet, incline slopes, all right, let's start by drawing a picture. All right, so here's your skier. And they go down the incline, and then they reach the bottom. And you know their speed at the top is 3 meters per second. And at the bottom, their speed is 15 meters per second. And you know that it's a 10-degree incline. Always start by drawing a picture. Drawing a picture works pretty well. So, now what? The deal here is that all slope questions more or less they're one-dimensional. So let's draw our axes here. I'll set the origin at the top. And they're moving along the x-axis. It's increasing. Okay. And so there's a variety of things we don't know. We don't know how long the incline is. This is going to be a constant acceleration question. Obviously, they're accelerating. But yeah, it's going to be a constant acceleration question. So the question here is, how do we tackle it? And the deal here is that constant acceleration questions are on a slope. The acceleration is g sine of theta. There's Calculon, old friend. So in this case, this is 9.81 times sine of 10. So that's going to be 1.70 meters per second going in this direction. Okay, so let's start cracking. We don't know what the final position is. The initial position is 0. So we can write out the constant acceleration equations pertaining to this situation. So x should be 0. You're going down slope, so that's 3.0 meters per second times time. And then the acceleration is down the slope, so it's going to be 1.7 over 2 t squared. The speed is going to be the initial speed, 3.0 meters per second, plus 1.7 meters per second squared times t. There's our equations of motion, as they're called. So how are we going to use them? We don't know what time they hit the bottom, and we don't know where they hit the bottom. So let's do that. The bottom, the speed here is 15 meters per second. So 15 is equal to 3 plus 1.7 times t bottom. So t bottom is equal to 15 minus 3 divided by 1.7 7.06 seconds. And so the position at the bottom is 3 times 7.06 plus 1.7 over 2 times 7.06 all squared. So the position at the bottom is 1.7 times 7.06 divided by 2, 63.5 meters. And there's the answer to question B, and this is the answer to question A. Well done. Move on to the next. Now, question 39. See if anybody has any questions. No questions on the thing. Okay. Question 39. A particle rotates in a circle with centripetal acceleration 8 meters per second squared. What is A if the radius is doubled without changing the particle's speed, or the speed is doubled without changing the particle's radius? This is a type of motion, this is a type of reasoning called proportional reasoning. You know, it's like a recipe. The recipe's like, hey, if this recipe, it calls for 2 cups of flour and we double the recipe, how many cups of flour do we need? It's a little bit more complicated, but in these cases, the idea here is by doubling one quantity, we can figure out whether another quantity quadruples or quintuples or whatever the deal is. So we know that the acceleration has the following v squared over r. I'm going to explain the reasoning in a bunch of different ways because there's a bunch of different ways we can think about this. But the idea here is we have a formula. I derived this formula in class, actually, using proportional reasoning. We said, hey, if we have 2 horses running around tracks, if one is traveling twice as fast as the other one, how's that going to affect the acceleration? It'll double it or quadruple it, etc. We did this in class. So we're going to apply a similar set of arguments for this. If A is equal to 8.0 meters per second squared before the change, if I double the radius, here, give me a second. Okay, so the ones are before the change, and the 2's here are after the change. And I want to find A2. Brute. So the first way I can solve this, let me do it the following way. The first way I can solve it is just by inspection here. If I double the radius, how is that going to affect this change? Radius shows up in the denominator, like that, to the power 1. So if I double the radius, I'll end up with an acceleration that's half as strong. And so that's going to be 4.0 meters per second squared. This type of reasoning is pretty fun. I'm not sure if it's your favorite type of reasoning. There's another way to do this, though, which uses proportions. And the idea here is A1 is equal to V1 squared over R1. A2 is equal to V2 squared over R2. In these questions, some things are held constant, it's held the same, and some things aren't. So in this case, V is the same. And what I'm going to do is I'm going to divide the first one by the second one. A2 divided by A1 is equal to V2 squared over R2 divided by V1 squared over R1, which is equal to V2 squared over R2 times R1 over V1 squared. These numbers in this case are held steady, so the relationship between A1 and A2 is the same as the relationship R1 divided by R2. we see that if I double the radius in this case, a2 over a1, if I double the radius, r1, so this is 2r1, I can represent the relationship between these two r's. Then it means that you can write a2 is equal to 1/2 a1 by cross multiplication, and you get the same result. That's one way to do it. The thing about reasoning in this way is that it's very, how should I say it? It's not all that straightforward. We're used to just doing the algebra, right? So if I just explain to you, hey, if I double r, how's that going to affect a? Plug in some actual numbers. It's not very hard for you to do that. The deal here is, though, that sometimes in an experimental lab, for instance, you don't know what these relationships are. You're not given an equation. All you're given is an experimental apparatus, and you do an experiment, and you'll look for relationships between the various variables that you'll be measuring, right? So in this case, you would control the values of v, double the value of r, and measure the different values of a. And you do it over and over and over, and then if you could prove that, let's say, a2 over a1 in your experiment had this relationship, then you could move from this to argue that a is some constant times 1 over r. You see? So thinking about it in this way, it's not the most helpful when it comes to doing problems, but it's actually fairly helpful in the real world, where somebody might say, hey, how long is it going to take for this to double, or some such question. Or if you become an experimental physicist, or even just generally, if you do experiments, this type of reasoning really pays off. The ability to turn this relationship into this equation. So part B of this question, without further ado, the speed is doubled without changing the circle's radius. So in this case, a1 is equal to 8. V2 is doubled v1. R1 is equal to R2. So the previous way to do this, the way I just showed you, this is fine. This is literally what proportional reasoning is, thinking like this, trying to build these relationships. That's proportional reasoning. If you're really, really clever, you don't need to do all this intermediate stuff. You can just jump right to this relationship. Because you're saying, okay, so A is proportional to 1 over R, and then so A1 over A2 is going to be equal to R1, R2. So that's helpful if you want to do it like that. If you can, you're cool. There's an alternative way to do this, though, and that's algebraic. A1 is equal to V squared over V1 squared R2. A2 is equal to V2 squared over R. Oh, wait, hold on. The deal here is I'm going to rewrite this expression until it looks like this expression. And I'm going to do it using these relationships. So the r's are equal, so the bottom is going to be still equal to r1. The top, this is 2v1 all squared. And so now this term has a lot of v1s and r1s in it, just like this guy, but it's not, something's not quite right. It's these parentheses. 4v1 squared over r1. So this is 4 times a1, so that's equal to 32 meters per second squared. Remember? Okay, so how should I put it? You might ask yourself right now, is there anything wrong with doing it this way, algebraically? There's nothing wrong with doing that algebraically. Algebra is actually a type of logical reasoning. It's a reasoning process. And so you can use algebra to do all this stuff that a person might do in their head and get the same answer. I don't care. Okay, so next question. That's 39. We just did 39. We have to do question 37. 37. And nobody's asked any questions in the live chat, so I guess everybody's happy. 37 goes like this. A CD-ROM drive in a computer spins the 12 centimeter diameter disk at 1,000 rotations per minute. RPM. RPM is a unit for describing frequency, but you know, you might hear that an engine goes around 400 RPM. I don't know, but if you think about those units, it's one rotation for per minute. Yeah, this is the 1/time unit units that we use to describe frequency. Oh yeah, so it spins at 10,000 RPM. What's the period in seconds? Oh, hold on. Hold on. Okay. So, 10,000 revolution per minute. So, if I take 1 divided by that number, it'll be in units of minutes per revolution, which is 1e minus 4 seconds. Or no, wait, minutes. The answer wanted me to write it down in seconds. So let's convert this to seconds. How do you convert minutes into seconds? You multiply by 1. Minute, second. There's 60 seconds is the same as 1 minute. So in essence, I'm multiplying by 1, but you know that the units cancel out here. So this is going to be 6e minus 3 seconds is the period. And the frequency in revolutions per second. So, okay, long story short, it's actually easier to convert period into seconds from minutes than it is to calculate revolutions, or the frequency, but it's not that much harder. 6e minus 3 seconds tells me it's frequency. 1 divided by 6e minus 3. You note that I keep writing rev here. Rev. You don't have to do that. A revolution is a unitless quantity. This is just to keep everything straight in my head. Not a unit. A revolution is not a unit. Okay, so long story short, the correct answer is 166.61 over seconds. Or 166.6 hertz. Hurt, don't it? Okay, so B. Speck of dust. Your dust is going around the circle. What's the radius of the circle? Radius of the circle is 6 centimeters. So the radius is 0.06 meters. So the circumference is 2 pi times r. Okay, so that's my radius, circumference. I know how long it takes to go around once. The distance it travels when it goes around once is this. The amount of time it takes is this. So the speed is the circumference divided by the period. 62.8 meters per second. That is the speed of a speck. Okay, so now I want to know the acceleration. I'm just going to plug it into v squared over r. So it's 62.8. Ooh, it's going to be big. Over 0.06. .57 E4 meters per second squared. We want that in terms of, all right, so the question is asking it in terms of G. You might have heard of G forces. G forces get used to describe, like, if you're testing an airplane or if you're an astronaut or something. The question is like, oh, how many G's can you pull? Right? A G-force is a multiple of the gravitational acceleration. It's a measure of gravity. That's what the G stands for. So it's just some multiple of 9.81. So 6.57 E4 divided by 9.81. That's, oh really? 6.57 E4 divided by 9.81. Huh. So it's almost 7,000 Gs. I think that's the answer. Yeah. Anyway, that's fun, right? Anybody have any questions? Yeah. So, you might wonder why this is, and it's because if you, because it's weird to talk about how much acceleration you feel as a multiple of G. And the reason comes down to your weight. In an accelerating reference frame, the idea here is that your weight is essentially your mass times G. So if you know how many G's you are pulling, quote unquote, so if your acceleration is 3 G's, it means that your body feels 3 times heavier than it should. If your acceleration is 9 G's, then 9 times heavier. So 6,000 G's, that's 6,000 times heavier. I don't know if Goku could withstand that, to be honest, but let's move on to the next question. Uh, 41. Question 41 goes like this. A peregrine falcon in a tight circular turn can attain a centripetal acceleration 1.5 times the free fall acceleration. If the falcon is flying at 20 meters per second, what's the radius of the turn? So there's a bird, and the bird is going in a circle. And radius, the bird has a velocity, 20 meters per second. We know the acceleration is 1.5 times G, so it's 1.5 times 9.81. Okay. And so this is equal to v squared over r. So it's 20 squared over r, so you can calculate what r is. Divided by 20 times 20. 0.036 meters. So the bird can do a 3 centimeter turn? That's bonkers. That can't be right. That's like the turning radius of the bird is. I think I looked it up earlier. They're about the size of a crow. 3 centimeters is like less than the width of a crow. So essentially, they can turn their body around in a complete circle. I find that hard to believe. These numbers must be made up. There's no way. 1.5 times 9.81, 14, 20 times 20 divided by answer. Oh, it's because I did the math wrong. I did the algebra wrong. I'm always telling you that the important thing here is that you remember to look to see if your answers make sense. Because sometimes they don't. And the reason is because you made a mistake. 27.2 meters. That's more reasonable. All right. Next question. Question 75. It's alive. 75 goes like this. A Ford Mustang can accelerate from 0 to 60 miles per hour in a time of 5.6 seconds. A Mini Cooper isn't capable of such a rapid start, but it can turn in a very small circle, 34 feet in diameter. How fast would you need to drive the Mini Cooper in this tight circle to match the magnitude of the Mustang's acceleration? Alright, well hold on. So 60 miles is equal to 100 kilometers an hour. So 60 miles per hour is the same as 100 kilometers per hour. So that takes care of that. Let's convert this into hours. Min. 1 hour is 60 minutes. And then min second, 60. And then kilometers, 1 kilometer is 1,000 meters. Let's convert this to meters per second just because it's easier to work that in. 100 times 1,123 divided by 3,600. 27.8 meters per second. Okay, so how much acceleration is the car at? The car goes from 0 to 27.8 in a time of... So we want to know what the acceleration is. 27.8 is equal to 0 plus a times 5.6. What equation are you using? That's a good question. This is the v is equal to v naught plus at equation. Constant acceleration. Now, acceleration is 4.96 meters per second squared. All right. 34 feet. I gotta look up the feet per meter. Feet into meters. I gotta look up the feet to meter conversion. So 1 foot is equal to 0.305 meters. Okay. So you got a car, and your car can go in a circle. What's going on? Stop being bad. Oh, come on now. Unfreeze. I don't know. Let's try swiping. No. Maybe if I swipe up. Ooh, that's cool. Notability. Close. All this stupid. What's going on here? Get back to work. I don't know how to unfreeze this. Let's just open a different program. Alright, that one. And full screen me. Okay. Ooh, what does that do? Okay. Good enough. We'll go with that. Sorry, technical issues. Everything's kind of settled down. Where were we? There was a car. It was going 100 miles an hour. 100 kilometers an hour times 1,000 or 3600. So the acceleration of the Mustang is 4.96. And the question was, what's the radius of the circle? It's given in 34 feet, and we want to convert that into meters. So, how do we do that? Let's see, where I looked it up before. What was it? Okay, 34 feet, so foot meter, I don't want to change this number, I want to change its units, so 1 foot is 0.305 meters, so that's 34 times 0.305, that's 10.4 meter in radius. So the question was, what's the speed? A is equal to v squared over r. 4.96 is equal to v squared over 10.4. And I plug this into my calculator. 4.96 times 10.4, square root it all. 7.18 meters per second. Someone wants something here. Yeah, there you go. Meters per second. It doesn't specify that it wants the answer in feet per minute or anything weird, so we'll just go with that. Okay, what's the next question? Next question is, let's see, that was 75. So the next question is page 131, question 5. Somewhere here is question 131. Page 131. Okay, 131. Question 5. Question 5 goes like this. If you know all the forces acting on a moving object, can you tell which direction the object is moving? If the answer is yes, explain how. If the answer is no, give an example. The answer is no. Let's give an example. Let's see. What's a good example? How about something? How about a hockey player? Okay. So, hockey players skate, FYI, by pushing off the ice with the blades of their skates. So let's suppose we have an example here. This guy is going this way. This guy is going that way. They're wearing helmets. Okay. So, this one, let's say they speed up. Which direction do they have to push off the ice to speed up? The answer is they have to push off the ice so that there's a force pushing them that way. So this guy wants to slow down. Which way will he need to accelerate to slow down? He needs to push on the ice in that direction. So this guy's going to turn his body so that his ice skates are digging into the ice like that to generate this force. In both cases, they're the same force, same direction, but in this case, the velocity is different. So even if you know the direction of the force, that doesn't tell you anything about the direction of the velocity. Next question. A carpenter wishes to tighten the heavy head of his hammer onto its light hammer. Okay. Hold on, let me drink some water. A carpenter wishes to tighten the heavy head of his hammer onto its light handle. Which method shown in question 4.7 will better tighten the head? Explain. Okay, well, I guess I'll just draw it. So here's one hammer. And here's the other hammer. And there's a hand involved. Let's draw your hand, I guess. So here's your hand. And you're bringing it down like that, or your hand is here. and you bring it down like this. In either case, there's going to be a shock. Essentially, there's going to be a force from the table. It's going to be a force from the table pushing up. Force from the table pushing up. And and the two different parts aren't all that well connected. Jeez. What's the answer to this question? I just glanced at it before assigning it. Because, okay, I'll tell you why this is a weird question. Let me just go into why I'm confused. This question's weird because essentially I think what it's asking us to do is compare how much inertia the hammerhead has compared to the hammer stick. But there's more to the hammer, there's more to the system than the hammer stick and head, right? There's like your hand, an arm, an elbow, and they're all attached. So if you've got a really good grip on it, then even though there's still two disconnected systems, the hammer and the hammer and the handle, which one has more inertia? I think the handle and the arm has more inertia because there's more mass in my arm than there is in a hammer handle, a hammer head. I think the answer they're going for is this one. Because in this one, the inertia of the moving hammerhead going down. In this one, the inertia of the hammerhead going down is going to push itself down onto the hammer. In this one, the handle also gets pushed down into the whole hammer, but I don't think they're counting your hand as part of the inertia. So I think in this case, it's supposed to drive further. But I don't know. Bad question. They say a good craftsman never blames his tools. But I tell you what, a lousy instructor can blame the question. All right. Are there any other questions? Anything you want me to do in the chat? You can list a question or two in the chat if you want to see me do it. Otherwise, I'll just doodle for a couple seconds, and if nobody has anything to say, I guess I will just leave. So, yeah. Go ahead and ask your question if you have one. Oh. Ooh. Okay. Oh, hey, look. Somebody said, can I go over the practice test posted on Connect? That's a good question. Yeah, okay. Let me boot it up. I mean, I guess it's not as fun as drawing bunnies and mugs, but if you want to see me do some practice questions on Connect, I guess I could. Alyssa has said, "Let me find a 2D kinematics question 1 second." I'll do the midterm book while we wait. Oh no, that's the review. Whoops. Practice. Oh, fun. What? What? What is this? Am I in? Oh, I'm in math. I'm opening a math folder. I'm like, why am I asking you guys to do integrals? Oh, snap. I forgot to give my math class an assignment this week. Oh, God. Oh, jeez. Okay. Focus. Midterm 1. Practice midterm. Okay, so I've got my midterm in front of me. I encourage you to get out a midterm in front of you. And I want to emphasize a couple things before we start. The first thing is that it's helpful to read through all of the questions before you start. In any of these midterms, there's always going to be a range of question difficulty, and there's always going to be a range of how much each question is worth. And you don't want to spend more time than necessary trying to solve a question that's hard but not worth very much. So some of the questions are going to be hard, some of them are going to be easy. You don't want to waste your time on a question that's hard and also not worth very much. So it's helpful to start your test by going through all the different questions, reading them, and then trying them. I bet that if I explain this online, I can probably get this done in about 20 minutes. Oh, I closed the window. Hold on. Okay, let's go. Question 1. Which of the following are not vector quantities? Oh, who needs to read this? Well, I guess I should read that. Okay, so I'll read this in advance. Question 1's which vector quantities? I know about those, so that should be easy. My dog starts. How much are these worth? Each question is worth 2 points. Okay. Dog starts at 100 meters, and I start at 0, and we run towards each other with some velocities. Where are we going to meet? Okay. I throw the ball into the air. So 2. That might be a relative motion question, or it might be a constant velocity question, which should be pretty easy. I throw the ball into the air. Which of the following statements is false? Those true-false questions are annoying. All right. Well, next. You're driving a car on a highway at a constant velocity of 100 meters per second. 100 meters per second? That's like 500 kilometers an hour. You find you need to apply lightly on the brake pedal to maintain your car's constant velocity. Oh, do you? Okay, so this is also got a force question. Explain in words what you mean by inertial reference frame. You guys don't know what inertial reference frame is because the textbook we were using is different from that one. I'll get back to that. Okay. Each question is worth number of points noted. You must share all your work to receive part marks and circle it. Okay. I stand on a cliff and throw an apple straight up above me at a bird. The bird's 10 meters above me, and the apple misses the bird and passes the bird moving at 3 meters per second. The apple lands at the bottom of the cliff 11 seconds after I threw it. Determine the apple's initial velocity. Well, that's fun. If my initial height is x and upward is positive, write the equation for the apple's position as a function of time. How far below me is the bottom of the cliff? At what time does the apple pass the bird moving upwards? How much higher above the bird is the apple's turning point? Oh, that's a good test. Oh, okay, question 2. Consider the following position versus time graph. It looks like when I scanned this test, I didn't have... I mean, this is a past midterm, right? So I must have drawn the graph in by hand at a later date and then given it to you. Huh. Okay, so I guess it's on us. We will draw a position versus time graph and then do the questions with it. Oh, jeez. Okay. Okay, so let's get cracking. Turn on your stopwatch. Okay, which of the following are not vector quantities? Let's see, position is a vector. Oh wait, yeah, displacement is a vector, yeah. Speed, not a vector. Deceleration, that's weird. Acceleration is a vector. So, I mean, we mentioned in class, deceleration isn't really a thing in physics. It's just a descriptor for acceleration. So these two are the answers. Oh, that's a bad way to write it. Question 2. Oh, blue. My dog starts at 100 meters. So these questions are always easier if you just draw them. my dog. I go this way at 4 meters per second. Goes this way at 6 meters per second. We can do this question with relative velocity, or we can do it just by describing the motion. X naught plus vt, right? Constant velocity, woo, motion. So my constant position, initial position is 0, 4 times t. The dog's position is 100 minus 6 times t. And so the question is, when do they meet? When does my position equal the dog's position? Because I'm going to go closer in this way, and the dog's going this way, and eventually we'll hit each other. 4t is equal to 100 minus 6t. So this is 10t is equal to 100. T is equal to 10 seconds. And so the question is, where am I at 10 seconds? So this is 0 plus 4 times 10. X is equal to 40. So the answer is A, 40. I throw the ball into the air. Which of the following statements is false? All right. You know, when you're doing these true-false questions, sometimes it helps to like just go through them and see which ones are true before. Easy true ones are easier to see than the false ones. It's hard to think your way through false questions. Okay, so what's true? It takes the same amount of time to travel from some specified height up to the apex as it does to travel down, right? So in other words, thing goes up, it comes down. Does it take the same amount of time to go from here to here as it does from here to here? The answer is yes. So that's a true statement. It is moving at the same instantaneous speed as I pass a certain height on the way up as on the way down. Yes, that's also true. Why is that true? That's true because if you draw the position versus time diagram, you always get a parabola of some sort. And the slope of this parabola tells you what the velocity is. And because the parabola has the same shape, this slope is the mirror image of this one. So they have the same number but opposite sign. So the speed is going to be the same. If traveling at a speed of 3 meters per second and 2 seconds before it reaches the apex, it'll be traveling the same speed 2 seconds after the apex. Yeah, did we just say that? Oh, I think we just said that. Acceleration of the ball when it's the apex is 0. No, the whole time it has constant acceleration. Whole time. Top of the arc, if it had 0 acceleration, it would just stop moving. And it just wouldn't be moving. But it is. I mean, it goes up and the velocity changes. So, so there you go. There's your answer. 4. You're driving a car with a highway with a velocity of 100 meters per second. Oh, that's funny. And you find you need to lightly apply a brake pedal to maintain your car's velocity. What do you do from this? Okay, so if you're traveling at a constant velocity, the forces must cancel out. That's something we've talked about in class. I don't think it's testable for the test, but we talked about it in class. I know that I'm applying a force forward. When you press on the gas, that applies a force on your car in the forward direction. So if the force is balanced, there must be another force pushing in this direction. So B, there must be some other forces pulling the car backwards. I guess pull is a weird word for it, but there you go. There must be other forces slowing your car down. Oh, the car has 0 acceleration. Okay. Next question. Explain in words what we mean by inertial reference frame and why we say Newton's first law will hold only in an inertial reference frame. You guys don't know what an inertial reference frame is because we haven't gotten there yet. because the order of the content when I ran this particular course is different than the one we're going through now. But the question here is, what's an inertial reference frame? An inertial reference frame is one where the law of inertia holds. Law of inertia says no force is equal to no acceleration. So if you imagine that you're on in the back of seat of a car and you're looking out the window, if the car starts to roll and you look outside, you're going to see all these trees, and the trees will move like that, and they're going to speed up over time. And so what you're going to say is, you're going to say, hey, look, all these trees are accelerating because in my reference frame, they're going that way faster and faster and faster. But the deal here is that you are in an accelerating reference frame, and that's why you're seeing weird things accelerate even if there aren't any forces on them. So that's what we mean. Oh dear. There we go. Long question. That's a pretty good long question. Stand on a cliff, throw an apple straight up above me at a bird. Here's a bird. Here's your cliff. Here's you. Stupid bird. You're going to throw an apple. Bird's height is 10 meters above you. And the apple misses the bird and keeps going up at 3 meters per second. And then it's going to go up, max height, and start coming down, go down, go down. It's going to hit the ground. T is equal to 11 seconds after you threw it. So this is a projectile motion question. It's super weird because you don't know what the initial height is, or rather you don't know how big this height is, and you don't know what the initial velocity is. So let's write down, let's set this height as the origin. X is equal to 0. Okay? And so let me write out the equations of motion just so I can demonstrate to you what I do and I don't know. You know, the acceleration is downwards, of course. So in other words, I'm going to do question B first. If my initial height's set to 0, then your position as a function of time is going to be 0 plus vi times t minus 9.81 over 2t squared. Okay. So, yeah. The big clue here is that you know that after the apple has gone up 10 meters, its speed is 3 meters per second. So, you'll note that in these equations there's a bunch of things I don't know. I don't know what time it is, or I don't know any specific time corresponding to a specific location. I also don't know what the initial velocity is, or the velocity at any particular time. But you note that you can combine these, solve for t, and replace, and you get final position minus initial position minus 2 times 9.81 is equal to v final squared minus v initial squared. So if you rearrange these, you see that you know what the change in height is. You know that it's gone up 10 meters. Oh, jeez. So this is minus, right in black, minus 2 times 9.81 times, you've gone up 10 meters. The speed after 10 meters is 3, and you don't know what the initial velocity squared is. So you can solve this for the initial speed. 2 times 9.81 times 10 plus 9 square root answer 14.3 meters per second. So that's your initial velocity, and so your position as a function time is 14.3 times t minus 9.81 over 2t squared. V is equal to 14.3 minus 9.81 times t. Okay, then, so that's part B. Part C, where's the bottom of the cliff? I know that it hits the bottom at t is equal to 11 seconds, so I can plug this equation into there to figure out the position of the bottom of the cliff. 14.3 times 11 minus 9.81 times 11 times 11 divided by 2 minus 436 meters. Man, I wasn't taking any prisoners when I wrote this test. Yeah. Well, how about that? That's pretty far down. Okay. These other questions are actually fairly simple once I've cracked the initial velocity. What time does the apple pass the bird going upwards? Well, I know that it passes the bird going at 3 meters per second. So I could use the fact that I know the position of the bird, and I now know all the terms in these equations. I could use this equation to crack it, but instead I'm going to use this. Oh, geez, that one. So 3 is equal to 14.3 minus 9.81 times time. So it's going to happen at 1.15 seconds. How much higher above the bird is the apple's turning point? Well, the apple's turning point is when its speed is equal to 0. So that happens at, oops. .46 seconds. And at 1.46 seconds, it's a position 14.3. 14.3 times answer minus 9.81 times answer divided by 2. 10.4 meters. So the apex is at higher than the bird. All right, next question. Considering the following position versus time graph. And I forgot to draw a position versus time graph, so I guess I'll just draw one. Does it need to do anything special? I guess it needs to go up to time t is equal to 8. So let's see. How about like this? That's fun. Okay. Okay, so describe the motion in words. I wonder what kind of diagram I had this one when I gave them this midterm. Move to the right for 2 seconds, then left at constant velocity for 4 seconds, then right for 2 seconds. Draw in the space provided the velocity versus time. All right. One thing you should keep in mind in this course is that this particular exercise we're doing comes from a non-calculus course. 2, 3. So it's a non-calculus course, which means that there's more of this graphing stuff to it. I mean, I guess that's an activity that we've done, but you know, I might ask you to just take a derivative because you can. All right, so what's the slope here? It goes up, it goes across 2 and then up 2, so its velocity is 1 for the first 2 seconds. And then it goes across 2 and down 3. So its velocity is minus 1.5. And then I guess from here to here it goes down by 2 because whatever, so that's fun. It's 1. And then it goes up to 1. Ugh. All right. Between t is equal to 4 seconds and t is equal to 8 seconds, what's the average velocity? T is equal to 4, the velocity is... Oh god, this is supposed to be a constant velocity question. Alright, minus 1 meter per second, and t is equal to 8, it's plus 1 meter per second. So the average acceleration is delta v over delta t. So that's 1 minus, oh, hold on. 1 minus 1. No, I did this right. Yeah, no, that's right. All over 4. So that's plus 2 over 4. So that's 1 point, nope, 0.5. The more you know. All right, so that's it for the question. How long did that take me? Did that take me 20 minutes? Pretty proud. Okay. So I guess one last question, which Alyssa Welchko wants to see page 104, question 31. So... Alyssa Welchko, this is a super great question. So, 31. So yeah, you might be wondering why I didn't upload more practice exams. And that's because all the practice exams I have are just old exams that we have. And every time you do an exam, you're doing it specifically for the material that you covered in that class, which might vary. Say 10 to 15% depending on the class, and then given that every midterm takes place in a different part of the year, you know, there's going to be another 10% different. So I mean, the test is going to be a quarter absolutely confusing to people who, you know, you'll read it and you'll be like, I've never heard any of these words before. And it's like, yeah, no kidding. This is last year's exam. Plus all sorts of other stuff like that graph that was missing. Oh, how embarrassing. Anyway, these online office hours are actually pretty good for questions. Question 31 goes like this. A rifle is aimed horizontally at a target 50 meters away. The bullet hits the target 2 centimeters below the aim point. What was the bullet's flight time? And what was the bullet's speed as it left the barrel? What a great question. Okay. So here's our gun. What do you mean I don't know what guns look like? They look like that. That's a pretty good gun. Oh, geez, you're drawing a 6-shooter. Not a... Oh, no. I drew a pistol instead of a rifle. Oh, well. So the idea here is... Here's where my target is. That's not... wait, at 50 meters away, right? 50 meters. That's not how the bullet traveled, though. The bullet took a path like this. Where this distance here is 0.02 meters. And the question is, what's the velocity? Okay, so this question sounds super difficult, but it's actually not as bad as it seems, because there's a trick here, and the trick is that the horizontal, that the x and vx evolve separately from the y position and the vy position. Okay. This is going to be some constant velocity, and this is going to be 0 minus 9.81 times t. Okay. Your initial height is 0. Your initial y velocity is 0 minus 9.81 over 2t squared, and this is going to be v0 times t. Okay, so here's the fun part. The fun part is that if say back here behind the target, foolhardily enough, I decide to, maybe there's a wall between us so I can't get hurt. I decide to drop an apple, say, okay? I drop an apple the moment the trigger is released. The deal is that the apple is going to move vertically the same way this bullet moves vertically. So when the bullet hits the wall, it's going to be at the same height as the apple the whole time. Does that make sense to you? And the reason is that the y components of the motion evolve independently of the x components of the motion. This is a quality of vectors and vector analysis, but the neat thing is, I mean, this is the motion for an object that's just dropped from rest, moving vertically. Okay? So, that's the clue to doing this, is that we don't know at what time it hits the wall, but we know the y position where it hits the wall. We know what that value is. So minus 0.02 is equal to minus 9.81 over 2 t hit squared. So t hit is going to be 0.004 seconds. It takes 0.04 seconds to go across. And that's enough time, because you know that this information still plugs into this. The amount of time matches up, right? So in other words, we know that the bullet's position at that time is going to be 0.00408. We know that the bullets traveled 50 seconds in that time, so we can go 50 divided by that. 12,262 meters per second. God, that's big. Did I forget to take the square root or something? 0.02 times 2 divided by 9.81. I did. I forgot to take the square root. You should always, always be careful when doing these questions. Ask yourself, does the number I get make sense? Because if the number you get doesn't make sense, you probably made a mistake. Alright, so this is 783 meters per second. And that seems like a reasonable bullet velocity to me. Alright, that's going to be it for today. It's been a pleasure doing online office hours, but nobody else has any questions, and I hope you have a good one. You should note that if you go to John Hopkinson's thing tonight, that'll be fun. You should note, though, that John Hopkinson asks very different types of questions than I do. So if you want more examples of the types of questions I'm going to ask, you also have the tutorials, which were written for this course specifically. So the tutorials should give you a pretty good example of what types of questions I might ask. Till next time, have fun. See ya.